Hi, my name is Pramshah, and I will be presenting the walkthrough of our high-risk project. The team who contributed to this project include myself, Luke Franchek, and Faiz Yusuf. The title of our project is High-Risk Medical Image Classification for Brain Tumors Detection using CNN and a Transformer Hybrid Model. Links to our GitHub repository and dataset obtained from Kaggle can be found here. Quick background information. Brain tumor detection from MRI scans is a critical task in medical diagnostics, where early and accurate classification can significantly improve patient outcomes. In this project, we developed a deep learning model that combines the spatial feature extraction capabilities of convolutional neural networks with the global attention mechanisms of transformer encoder layers. In medical analysis, the combination of transformer designs and CNNs has attracted a lot of interest, especially for the detection of segmentation and brain tumors. The first study, TransXAI, which is a hybrid model combining CNNs with vision transformers to enhance glioma segmentation in multimodal MRI scans. The second study presented a hybrid model integrating CNNs with vision transformers for brain tumor classification tasks. Here's a quick breakdown of how we conducted the work for this project. To start off, we altered the images to the same size and used a 3-channel RGB format. Data augmentation techniques such as random horizontal flipping, rotations up to 15 degrees, and color jittering was then added to improve data generalization. The dataset was then split. We opted to use 70% for training, 15% for validation, and 15% for testing. Moving on to our model architecture, we are using a hybrid model with a CNN feature extractor alongside a transformer encoder head. We used a modified version of ResNet 18 as the initial feature extractor. The convolutional layers extract spatial features and reduced image sizing through sequential downsampling. Final convolutional feature map has a shape of 32, 512, 7, and 7, where 32 is the batch size. The CNN output is flattened and transposed into a sequence of 49 tokens with 512 dimensions. A learnable CLS token is preceded and positional encodings are added. The sequence is passed through 3 transformer encoder layers with 8 attention heads, and the final CLS embedding is normalized and used for classification via linear layer. Following 25 epochs of training, we assessed its performance using the test dataset. The model's 98.4 test accuracy provides compelling evidence for the efficiency of merging transformer-based and convolutional architectures in the diagnosis of brain tumors. With no significant indications of overfitting, we saw steady gains in training and validation accuracy throughout the training process. We also looked at the confusion matrix produced during testing. The model accurately identified 22 tumor images and 12 non-tumor images. It also misclassified 4 tumor photos as non-tumor and 1 non-tumor image as a tumor. Given that false negatives are the most harmful errors in medical testing, the comparatively low rate of false negatives is especially promising. To prevent misdiagnosis, cancers must be detected when they are present, and our model excels in this area. The model's precision was 0.95, meaning that the great majority of photos that were classified as tumors were indeed accurate. The model sensitivity or recall was 0.91, indicating that it could detect real tumor instances. The model's overall reliability was highlighted by its F1 score of 0.93. Furthermore, we plotted the ROC curve and calculated the AUC. As seen in the plot, the model achieved an AUC of 0.97, indicating excellent separability between the tumor and non-tumor classes. The ROC curve hugs the top left corner of the graph, confirming that the model maintains a true positive rate while minimizing the false positives across different classification thresholds. To conclude, our results demonstrate that hybrid architectures can significantly enhance performance in medical image classification tasks, especially in domains where both fine-grained texture and holistic spatial reasonings are essential. This success not only validates our design choices, but also contributes to a growing body of evidence supporting the adoption of transformer-based models in the medical imaging field. Further developments include extending our model to multi-class classifications such as differentiating between glioma, metaglioma, and pituitary tumors would increase its clinical utility. Additionally, incorporating segmentation capabilities could allow the model to localize tumors within an image, aiding in surgical planning and treatment design. Implementation of GradCam or attention heat maps could help classify which images influence the model's decision, increasing trust and transparency. Furthermore, evaluating the model on more diverse and heterogeneous datasets, including machines from different MRI machines, clinical settings, and patient demographics, would ensure broader generalizability. Thank you.